We calculated work and power for translational systems. Work was equal to the integral of F dot dr, and power was basically, if we have a constant force, we could say that power is equal to force times velocity, or power was the work done divided by the time. What about rotational motion? Rotational motion, we know, has kinetic energy. So essentially, if something is rotating and has kinetic energy, we should be able to do work on it in order to change its rotational kinetic energy. Okay, how do we come up with an expression for work and power for rotational motion? Well, I can take a guess here. Because we just replaced our translational quantities with rotational quantities when we came up with kinetic energy, I'm going to guess that for work, I can just take, instead of the integral of F dot dr, the integral of the torque dot d theta here, okay? For power, for a constant torque, instead of saying power is equal to force times velocity, maybe it's equal to torque times angular velocity. All right, let's see if we actually get that when we try to derive this. Now, again, remember work. Work is equal to, due to a conservative force, is going to be equal to F dot dr. All right? So essentially, if it's a conservative force, it's path independent. If it is a non-conservative force, then we have to, consider the fact that the path will create our, an overall effect to what we're doing. The distance that we travel will influence the overall work that's done for non-conservative force, is what I'm trying to say. So I'm going to change this dr to ds, which ds represents how far we've moved some mass on a disk along. And we have to take every point on the disk and integrate over the entire thing to get the overall work done to each part. So here, F dot ds is a dot product between the force and an infinitesimal displacement on the disk. So again, not that, could have been done a little bit better, but let's say at this point is moving from here to here. The work done on this point will be equal to the force on that point, dot ds. And again, S is equal to, if we're thinking about our different directions, the radial direction, it is the cross product between the angular displacement and the radial displacement. So here we have ds is equal to d theta cross r. If we actually break this down, our first term is right here. We take the derivative of d theta cross r, and the theta cross dr. By the way, folks, if we're thinking about the theta direction, by the right-hand rule, any rotation actually is in this vertical direction here. That's why my cross product, r is going this way and ds is going this way. Now, because this is a rigid disk, dr is going to be 0. There's going to be no change in the radial distance here. So this term is going to drop out. So ds is just d theta cross r. And again, just thinking about the direction, this is going to be in the tangential direction. This is going to be in the same direction as the axis, same direction as the angular velocity, same direction as any torque that I have on there. Okay, so now dw, the infinitesimal amount of work done by a small rotation, is F dot ds. We've already said that ds is d theta cross r. So dw becomes F dot, now we're going to replace this with d theta cross r. We have to do a little vector identity here. A dot b cross c is the same as b dot c cross a. That's going to allow me to get rid of this right here and replace this with F cross r, which is going to be important because that's going to be related to the torque. So actually reverse that. It should be R cross F. But basically, we're trying to get just a quantity here, so we'll ignore that little faux pas. dW equals d theta dot F cross R. dW then becomes d theta dot uh, tau, okay? And in this particular case, the work done from our initial angle to our final angle becomes tau dot d theta. So what this tells me is if I put a torque on a disk, okay, this is exactly what I expected to get. If I put a torque on a disk, okay, if I integrate tau dot d theta, really how much we're rotating this here, that'll give me the total work done here. Now, if tau is a constant, I can bring tau out in front, and then my integral just becomes the integral of d theta. So this just becomes the work done for a constant torque is equal to the torque times the angular displacement. All right. So exactly what I expected. If we had a constant force, work is equal to force times distance. For a constant torque, our work is equal to the torque times the angular displacement. So for instance, let's say I have a torque of 10 Newton meters, and I rotate the disk a distance of 2 pi, okay? One full rotation. Then I would have 20 pi joules of work done to rotate that disk. All right. The more torque that's required to rotate the disk, the more energy that's going to go into it, or the more work I'm going to do against a non-conservative force. So I could say, okay, given a certain amount of torque, how much kinetic energy will the disk have after I put into that, or how much will that change? I can get that just simply by taking the torque times how much it's rotated. All right. It makes sense too, because the more torque I put on the disk, the more energy it's going to gain, the more work that I'm going to do on it. And the longer I have the torque on, causing the disk to rotate a greater and greater angular distance, again, the more energy it's going to gain from that work being done. Conversely, if I want to slow that disk down, I can put a negative torque on that. That's going to take kinetic energy out of the system and slow the disk down. But again, the work done on a rotating disk is simply torque times the angular displacement, given that that torque is constant. If the torque isn't constant, then if the torque is a function of the angle, I have a more difficult integral to do here. What about power? Okay, what about power? Let's take what we had before. We're going to say dW is equal to an infinitesimal amount of torque times d theta here. Well, we can say that power is equal to dW dt. That's its definition is the rate at which energy is converted per unit time. If I'm taking this right here and replacing this for a constant tau, okay, let's say that our torque doesn't change during this process, I can then say that it's d theta dt. We recognize d theta dt is omega. So the power for constant torque is going to be equal to the torque times the angular velocity. And again, that's what I expected. Power was equal to force times velocity for translational motion. Power is equal to tau times omega here. Now, if we look at an engine, we know that for an internal combustion engine, the power will actually increase up to a certain point at which the engine starts rotating so quickly that your losses start exceeding the amount of power that you can get out, and your power curve sort of turns over like this. Okay, basically for an EV, the torque is pretty level, so we'll use an internal combustion engine here, but we can clearly see that the torque that we get out of the engine actually peaks much sooner than the power, and that makes sense because of this. The torque goes by the power divided by the angular velocity. As we go faster and faster, as long as the power is increasing faster than the angular velocity, we will get more and more torque. But soon as that rate of increase of torque can't exceed the angular velocity increase, this starts going down because, again, torque is power divided by angular velocity. So here we can see for this engine, we're going to get the most torque at about 3,500 RPMs. But if we go any faster, our torque actually begins to decrease before the power even peaks here.